Hi, I'm Tony Minshall. I'm an application engineer working with Teledyne LaCroix, and I'm going to be talking about high-resolution oscilloscopes. Hi, good morning. I'm Tony Minshall from Teledyne LaCroix. I'm application engineer looking after scopes in the instrumentation division. So LaCroix used to be a standalone test and measurement company until a couple of years ago when we merged with Teledyne. So now we're part of the instrumentation division of Teledyne. Okay, I'm going to go through, this is going to be quite a technical presentation about the 12-bit architecture and the advantages that that gives you in your measurements and in your R&D. So if we look at, go back to the beginning and look at analog oscilloscopes, this is what we had sort of about 40 years ago, maybe 30, 20 years ago. Recently, of course, digital oscilloscopes have evolved. And what's happened with the digital oscilloscope is brought a lot of extra accuracy to the horizontal time. So instead of having a 3% inaccuracy, which you'd have on an analog scope, you're now down to 0.001%. So it's a far more accurate horizontal type measurement. But when you look at them vertically, the analog scope and the digital scope are very, very similar in their vertical accuracy. So typically the analog you'd have 3%, and the digital you'd maybe have 3%, 2%, somewhere in that order, with the majority of scopes that are out there. So a couple of scope basics. There's lots of different things which are talked about. So there's bandwidth, and now we have developed, or in the market has developed, scopes with very, very high bandwidths. So 65 gigahertz and beyond. So very high bandwidth scopes available. Same with sample rate. There's now sample rates out there in the hundreds of gigahertz, so very, very high sample rates. And then when we look at record lengths, we now have acquisition record lengths in the mega points, so very, very deep acquisitions. But when we look at the ADC, the input resolution, we can see actually that's not changed a lot. So when the first digital oscilloscopes came out, they were 8-bit. And where are they today? Well, almost all of them out there are still 8-bit. So there's been very little movement over the years in the development of the A to D in the oscilloscope. So the A to D gives us much, much better resolution. So what I'm going to do is talk about resolution. So what is resolution? What does it mean? Well, resolution is changing around us all the time. So if I give you a couple of examples, we've got the iPhone. Okay, so when we got the iPhone 4, it had a 4 times improvement in the display over previous generations. So that's an improvement in the resolution. If we look at digital cameras, they've gone from very low resolution now up to something like 15 megapixels. So you've got 5 times or more resolution improvements. And if we look at television, you've got the standard definition through to HD TV, and you've got a 6 times improvement. So resolution is improving around us all the time in many different areas. If we take an example here, we've got a simple example of a thermometer. On the right-hand side, you've got, if you like, a low-resolution scale. And if you had to read off the absolute numbers off there, you can see you've got a fairly low resolution. Whereas on the left-hand side, you can clearly see you've got much finer granularity. You're going to get better measurements. And that's what it's all about. It's all about getting improved, more accurate measurements. So resolution in the oscilloscope is down to several factors actually. Primarily, obviously, each factor can be limiting, but there's the A to D converter, which is typically 8-bit, but there's also things like the input amplifier, the noise on the power supply. So when developing a high resolution system, it needs to be a system design, not just the A to D, but that is obviously an important point and has been the limiting point for many years. So if we take a look here, LaCroix have got some high bandwidth scopes. So this one is typically up to 1 gigahertz bandwidth, 2.5 gigasample, with 16 times higher resolution. So what does 16 times higher resolution mean? Let's have a quick look at that. So here we've got an example. You can see on the left-hand side there, I've got an 8-bit example, and I've got a very light trace in there. Okay, and I'm tracking that with my 8-bit A to D, and what you would actually see is the dark blue trace. So you can see fairly heavy heavy lumps there, whereas on the right hand side I've got the light blue and the dark blue is following it much closer. So how do we get the 16 times? You can see at the top the math there. It's the A to D at 2 to the power of the number of bits. So an 8-bit will have 256 discrete levels across the screen, whereas a 12-bit is 2 to the power of 12, 4096, multiply one into the other and you get the 16 times. So it's straightforward. Okay, I've got a couple of other things here. Obviously it means that your quantization levels are much smaller, but also potentially your jitter. Because if you look on the horizontal domain there, you also have some, I should have brought my laser pointer, that would have been great. But is there a laser pointer on here? Not sure, I'll leave it alone. Okay. Middle button, okay. So you can see here you've got a bit of jitter. So not only do you get an improved quantization, but potentially you get improved jitter at the same sampling rate. And here I've just done the math, added the math in here. So you've got a DC gain accuracy and those sorts of things. And that relates here into measurements. If I look at my full scale measurements. So on the left-hand side, you've got the full scale, okay? So, and then you've got the smallest voltage step that you can achieve with either the 8-bit or the 12-bit. And you can clearly see the granularity improvement. So at the 8 volts that's being used as an example there, you've got 31.3 or 1.95. So you can obviously see the advantage to that. So how does that look when we look at the waveforms themselves? Okay, well, I've got a waveform here, looks pretty good. This is actually on an 8-bit, looks pretty good. So if we look at that on a 12-bit, you find it's that much thinner. So it just crisps everything up. So your waveforms are much cleaner, much crisper. But what it also means you get a lot more accuracy in your vertical measurements. A lot of scopes are having these features these days where they're saying they've got built-in multimeters in them. They've got a little display on it, says it's a built-in multimeter, but that's typically using the accuracy of the 8-bit A to D. So they're not actually very accurate. Whereas with a 12-bit, doing that kind of thing, you get a lot more vertical measurement accuracy. So we can see it here just in baseline noise, an 8-bit and a 12-bit. 12-bit having much lower baseline noise. And I've highlighted a couple of the values over there, so you can see the values. So you've got 214 microvolts compared to 98 microvolts. So you don't actually get a full 16 times improvement because, as I said earlier, you've got things like the power supply, how good is your power supply noise suppression, how good are your amplifiers, and all those sorts of things. So you don't actually get the full 16-bit, but you get significantly more than you will with an 8-bit. Here we can see it. If you're doing an FFT or a spectrum measurement using a 12-bit, you'll get a lower noise floor, you'll get lower spurs. And I've got a couple of examples here. Here's a multi-tone captured on an 8-bit and a multi-tone captured on a 12-bit. So you can see the advantage of this technology. And likewise, I've just put them up there with a couple of markers on so you can see the difference there. And if I look at waveforms themselves, how does it show itself? In this case, I've got a fairly noisy waveform on the left-hand side, same waveform on the right, and I can clearly see on the right, I can see the different spikes and the different noise on there. I've got some better examples than that, actually. I've got some examples. This is quite a good one. I'm looking at the fine ripple on this square wave. So I'm using this is just an example waveform. I've got a square wave here with a diminishing sine wave on it, and if I look down in one of the sections here and try to measure the ripple on that, then you can see on the left hand one that you can actually see the quantization level, you can see the discrete levels of the A to D, whereas on the right hand side, if you were measuring that with the same settings, you get a far more accurate measurement. If you did, for instance, the peak to peak voltage across there, on the right hand side you're going to get something that's way more accurate than on the left hand side. This is a shutdown of a circuit. So I've got a circuit that's shutting down here, and I'm looking at what's happening right at the end. Bit of a strange shape I've got there. So I'm looking at what's happening at the end. I did it a couple of times with the two different types of scopes. And by the way, they're both LaCroix scopes. So LaCroix makes 8-bit scopes, and we also make 12-bit scopes as well. So it's the two. This is off. All of this is off different types of LaCroix scopes. So you can see the shutdown on the left-hand side. You can clearly see the A to D levels, whereas on the right-hand side, you can see the shape of the waveform. You can make some meaningful measurements on that. So it's giving you the fine granularity when you've got, particularly when you've got large voltages. And this is just showing the key about this slide here is the bottom right-hand corner, where you've got the measurement of the peak to peak. So I've got 165 and I've got 134. That's actually relatively close. If I were to move along and measure further along, then you find that the 12-bit actually moves further away than the 8-bit, because the granularity, the ratio becomes much larger. So you find those numbers actually get worse as you move along to lower level waveforms. So linear averaging. So this is something which can be done. So 8-bit versus true 12-bit. So one thing you can do with an 8-bit to clean it up, you can do something called linear averaging. It's like a boxcar average. So you move it along through the waveform, as I've got here. So you may have the red waveform as being your original, and then the blue one there would be the boxcar averaged. And what it does is it effectively reduces the bandwidth. That's what happens. So quite often what you might do is use a very high speed A to D to try and improve the bandwidth as much as possible. But then what you're doing is you're not capturing real data, you're capturing mathematically interpolated data. So sliding horizontal average, reduction in number of samples. Some people do it pre-acquisition, which means it can't be undone. So you might see this called E-res or high-res. So sometimes it's pre-acquisition, sometimes it's post-acquisition. LaCroix have this capability as well, and we have it post-acquisition. What does that mean? That means you can turn it off and see what the original waveform looked like. With a pre-acquisition, which is done by some people, it's not possible to turn it off. Once it's turned on, you're stuck with the result. So pre-acquisition processing cannot be reversed, and the post-acquisition can be reversed. And then you get a loss of bandwidth because it is a horizontal averaging. It's done on a single acquisition. Okay, here's a couple of examples here. I've used a LaCroix 8-bit scope. It's running at 40 gigasamples, and I'm applying some different things so you can see what's happening here. So I can apply additional bits, and these additional bits are linear averaged. And you can clearly see over there that I've got my plus 3 bits, I've got minus 3 dB of 320 megahertz. So I'm having to run a very, very high A to D rate to get a relatively low bandwidth. So that's taken an 8-bit up to an 11-bit. So that's where it's taken it to. And you can see it at different settings there. So I've got 40 gigasample, 20 gigasample, and you can see the number of bits, plus 1, plus 2, plus 3 in there, and see how that limits the bandwidth. So it brings the bandwidth down, but it improves the noise. So that's one method. And we can see it here. Unfortunately, this isn't going to work. I don't think that's going to work. There's a little macro that runs with that actually allows me to adjust these, and I can see how the bits work. But basically, if I just explain it from here, the top part is it's just showing the tracking with a 12-bit, and the bottom one shows it with an 8-bit. But what that macro will do, which will be available because you'll be able to download this, you can run that macro, and when you run that, you'll be able to adjust the lines, and you'll be able to apply linear averaging as well. So the macro allows me to apply linear averaging, and then you can see the linear averaging results in there as well. So here's a quick look at a linear average. So at the bottom you've got a linear average, at the top part you've got a 12-bit. So it definitely gives you higher performance than you get with a raw A to D, but it's still not as good as the 12-bit. How about repetitive? So you can average in a repetitive mode. Okay, so I've got a square wave, got noise on it. I just use instead of using a linear average, I use my multiple acquisitions and average those, which is what I've done here. So I've taken the yellow trace, which is unaveraged, and you can see the noise on that, and I've taken the red trace and I've turned the multiple acquisition averaging on, and that works really well. that really helps to improve the the resolution and gets rid of a lot of the noise, and that looks like the magic answer. It doesn't always work though. It doesn't work if you've got a waveform that is not repetitive. So if I look at my bottom waveform, and that's actually an I squared C waveform I'm capturing there, it's not repetitive because the data keeps changing. So if I average that, as I've done in the top, you can see it just scrambles the data because the data's not repetitive, it's changing, the address is changing, the payload's changing. So when you're using an average technique, it can only work if you've got a repetitive waveform. If you've got something which is changing, as in here, or any kind of sweep, then averaging just doesn't work. So as I put down at the bottom there, can't be used on runts. If you had a runt, if you were trying to find a runt, which is like a waveform that comes up and goes down, doesn't go to the full height it should, and then come back up, if you do any kind of averaging, you'll just take that out, you'll average that out. Glitches, any of those sorts of things, you just can't use it. So let's have a look at a real world example. I've got 4 examples, but I've only put 1 on here, which is good because we don't have too much time. And this is power measurements. So if we take a power supply, I've got a switch mode power supply here, lots of different measurements that I need to do on here. Okay, some of the more difficult ones are things like the RDS on, so the conduction resistance of your silicon switch. And that one is really challenging. So here I've got a 12-bit scope, I've got a differential amplifier, I've got current probes and high voltage probes and other things. I'm taking the measurements here. So if we have a look here, so transition losses, so this is just the general measurement. So I've got the voltages there and I've got the transition, I've got the voltage and the current. The voltage is in yellow, the current is in blue, and then the calculated losses are in the orange on the lower part of the trace. You can't read the values there, but what you'll find is that this is 50 volts per division. So we've got 50 volts per division across here, and then we're calculating out and we can see all the losses in there. But that's not the key point. It's really when we get down to things like when you start to do this RDS on type measurement, you can see that on the 8-bit, when we zoomed to do this, you can see the granularity is so poor that you can't actually do that kind of measurement. Okay, so we've zoomed down to 2 volts per division from 50 volts per division. And when you do it with a 12-bit, obviously you're going to, you get a much better result all the way through. Okay, so it's clear the advantages in here. It's key to lots of different kinds of measurements. This is one example. I've got some more examples, but I haven't really got the time to show you those. But if you're doing anything with modulation or video or anything which has a lot of vertical accuracy required, then this really does make a difference. This is the RDS on that I was talking about. This is interesting. So now you can clearly see that it's 50 volts per division we've got on the top here. We're doing the measurement, and what it's doing is multiplying out as the voltage gets down to the 0, okay, and then it'll do the calculation for you and tell you exactly what that resistance is. If you try and do that with an 8-bit, and obviously we make 8-bit scopes as well as 12 bits, you'll find you can't do that with an 8-bit. So one thing that people try and do is that they try and increase the volts per division. So they say, well, okay, if I need to make this fine measurement, how do I do it? Right, we won't have 50 volts per division, we'll go down to 20 volts per division or 10 volts. As you go down to a lower voltage per division, your A to D is spread out over a lower range. So you can get close to doing it. But the problem with that is then you've got, what we've got about, I don't know, 460 volts or 480 volts there approximately. But if you go down to 10 volts per division to make that fine measurement, you're feeding 480 volts into your front end, which is only set to 80 volts per division. So you overload your input amplifier, you can potentially damage your input amplifier, so you end up with front end overload. And that's something I've seen quite often. So people doing these sorts of measurements, such as power type measurements, where they need to do this type of thing, then they find the 12-bit scope very, very useful. Here I'm just doing I've got a bunch of cycles running here. I'm just doing the turn on, turn off. So I'm just doing some basic cycles here. But for this kind of thing, the accuracy of the 12-bit really does help. This is an RDS on, so I'm just going through a couple of the power measurements that can be done. Sorry, this is not RDS, this is the safe operating area. So what I've got is I've got a load of voltage cycles at the top, current cycles below, and the scope's just calculating what the safe operating area is. And by having that accuracy, you've got a very accurate XY graph there on the right-hand side. The XY graph shows the safe operating area. It's also maskable, so all you can do is you can put a cursor on it and see, am I getting close to exceeding my safe operating area? And I've got some statistics at the bottom as well. This kind of thing, you know, we think about doing this measurement, okay, it's straightforward to do, but if you're making a switching power supply, you need to think, well, actually it's got to work from what? From 85 volts to 270 volts. Because it's got to work in Japan, it's got to work in the UK, it's got to work in the US, so it needs a wide range, and it also has to work under different load conditions. So when measuring these, obviously you need to measure it with different input voltages, but also different loads, full load to low load across all those voltage ranges. But that's just a little bit on power. So DC to DC converter ripple. Still focusing on power, the 12-bit allows us to take those ripple measurements. So I've selected ripple at the bottom there. I've got my mean, my peak, my max, my min, and I'm doing a spectrum of that so I can see where that is, and I've got the frequencies and the amplitudes read out at the top. So it's having a high DC offset, but also having the fine granularity to be able to see the noise that's on there, and then you can do these types of measurements. So this sort of thing is really an area where the 12-bit really exceeds itself. So we've seen this already, so this is just the showing the low voltage end, and this is, if you like, a summary of the power measurements, why somebody would use it in power, for instance. But there's a lot of us not doing power. And so there's lots of different applications where it's very, very beneficial. So here's some for you. Others, as I said, are video. I've done quite a bit of work in the video area, and there's a video company not far from here actually who uses our scopes because they need to see that fine granularity. I haven't put any of their stuff up here. So it's used throughout industry, and it benefits anybody who needs to make any vertical measurements. The question which a lot of people want to know is, isn't that going to cost me twice as much? That's always what people think. They think it's expensive, and actually it's not. When you look at the LaCroix range, this is actually our second generation of 12-bit. Our first generation, yeah, we were learning, and it was, you know, a more expensive product. This is our second generation we're into now, and the price has come down dramatically. So this is very slightly more expensive than an equivalent 8-bit, but you're not talking twice as much. You're not talking 16 times as much. So just to round off then, yeah, we have 12-bit A to Ds, which do have the linear averaging, which can take them up to 15 bits. We have bandwidths up to 1 gigahertz, okay? Why only 1 gigahertz? Why don't we do it at 4 gigahertz or 20 gigahertz? Because actually the A to D technology to do 12 bits is very difficult to do, and you have to have your A to D running that much quicker. And at the moment we don't have A to Ds which are running at 40 gigahertz or 80 gigahertz. So at the moment we're limited very much to 1 gigahertz bandwidth. But all of the low frequency type measurements, and there's an awful lot of them, so 1 gigahertz and below, have the advantage of having 12-bit technology available. Obviously long memory, touch display. A couple of options which benefit from this is obviously the power, which we've seen already, but also spectrum analyzer. If you've got a scope, you'll have like an FFT built in. Okay, an FFT is in just about every scope you can buy has an FFT built in. What we've done with the 12 bits is we have the FFT, but we also have a spectrum capability which really takes advantage of the 12-bit and optimizes that for frequency-based measurements. So we can use that 12-bit to improve a spectrum type display on there. So we've used the logo HD 4096, high definition, 4096 bits. combination, as it says up there, of good A to Ds, but also very good signal to noise ratio amplifiers. So careful architectural design of the front end, very low noise very low noise power supply system. It has to be, otherwise obviously that feeds straight through. And benefits: clean, crisp waveforms, more signal detail, precise waveform measurements. Any questions? Well, yeah.
Hi Tony, thank you for the presentation. I just want to know what's the major problem preventing this technology from 8 bits to 12 bits and to achieve the high bandwidth, because you see with this 12 bandwidth stop at 1 gigahertz bandwidth. So I want to know what can be improved beyond that. I mean, with the help of 12 bits machine.
Well, if you're doing, for instance, communication links, when you're doing eye diagrams, those kinds of things, if you're on a high-speed link, we're doing eye diagrams and jitter measurements and those sorts of things today with 12-bit on high-speed links. Sorry, with 8-bit on high-speed links. When you look at those eye diagrams, because it's 8-bit, there is a contribution to the vertical noise of the 8-bit, so you don't get as good an eye diagram as you could do if you actually did have 12-bit. We don't have it, but from the other things we've done, we know that we will get more accurate measurements on communication links and things like that. So higher speed things like radar, for instance. If you're working up there and you want to look at chirps and chirp bursts up in the gigahertz range, you can't do that repetitively because the burst is a changing frequency, and it's difficult to get a good trigger and do that in you can do it in 8-bit. That's the only way we can do it today. So, but the 12-bit would give you much finer granularity particularly for things like reflections. So if you're sending out sonar or well, you can do it with sonar because it's low frequency, but if you're doing it with high frequency radar, then you're limited as to what you can get back because of the granularity, because the reflection is a lot lower. So it's that sort of area. Yeah. Well, we've got one at the back, which is not turned on, but I will turn it on in a moment. So anybody who wants to look at it, come and have a play, and we'll have a look, and you'll just see. It's just like a normal scope. It's just a lot more accurate.
Sorry, I had a late question.
Yeah. Okay.
You mentioned spectral analysis.
Yeah.
And you also implied that is derived from the essentially the A to D bits, etc.
Yes.
Does that, so there's two rider questions. So firstly, that implies it's not real-time spectrum analysis. And the second question is, if you've got a scope and you're looking at signals, what does the spectrum analysis give you extra? So it's, what application does it serve?
Okay. Right. Okay. So it's not real-time as the first question. Okay. So with a traditional spectrum analyzer, you've got a swept measurement. Okay, this isn't like that. This is a broadband measurement, so it acquires a broadband memory and then does the math on that. So it's not a swept measurement. Okay, and then of course it updates at whatever rate it can process the data at. So as far as real time is concerned, it is, if you did a single shot, for instance, you could do a single shot real time of an entire bandwidth, so say for instance a chirp. And you could do it just one acquisition and do the whole thing, and that would work. The disadvantage, of course, with that method, the advantage, of course, is the broadband nature, but the disadvantage is that because it's not swept, you get more noise through, so you cannot match the performance of a true spectrum analyzer, because its swept nature just produces much better performance than you'll get with a broadband measurement. But it's significantly better than you'll get with an 8-bit scope, for instance. You've got full control of things like resolution, bandwidth, and those sorts of things. So your question was, the other question was, I think it was, why have spectrum in a scope? Is it?
What are the applications?
Okay, the applications. Right, the applications are, a lot of people need to know the frequency content of whatever they're looking at. So quite often you have a spectrum analyzer in a lab, and it's just a way of adding functionality, high value functionality really, to something that you're already purchasing for your bench. So it is an option. So if you don't see the value, or you already have spectrum analysis or spectrum analyzers, you don't need to have it. But if you do want it, or if you can't spare the bench space for a spectrum analyzer, or if you don't want to pay for a load of hardware again, you've already purchased a load of hardware and you just want to add on functionality, then it's a very low cost way of adding a lot of functionality. Now, if you compare that against an FFT, it's kind of different. We do an FFT. You get the display out. So do you have tracking cursors or tracking markers that track all the peaks? No, you don't. Does it update very rapidly? Maybe, maybe not. You have to control the memory yourself. There's a lot of things you have to do to actually optimize an FFT. If I put the spectrum on there, you'll find you've got tracking markers, which will just go on there and find all the peaks, give you all the readouts of all those peaks. You've got harmonic things. So you can do a lot more with it, basically.
Okay, thank you.
Okay.